Hello, everyone, and welcome to today's webinar. I'm Zlata from the FJD Trion team. Thank you all for joining us for this webinar on contour maps and QGIS workflow with FJD Trion. In today's session, we'll explore how contour maps can be created and processed and how FJD Trion Solutions can support this process in real applications. We hope that this webinar will give you useful insights and practical ideas that you can apply in your own work. We're also very pleased to be joined by our special guest, Nick from Scanflow Solutions, together with his team. And also, this webinar is part of a broader QGIS workflow webinar series, so stay tuned for more sessions to come. So let's get started. And now, Nick, I'd like to invite you to introduce yourself and your team.
Welcome everyone, and thank you for joining today. Let me start with a simple idea. A point cloud can contain millions of measurements and still fail to explain the terrain clearly. And that is exactly why contour maps still matter. Because no matter how much data we capture, the real challenge remains the same. How do we turn complex terrain into something people can actually understand? That is what today's webinar is about. We're going to look at how raw LiDAR data can be transformed into a contour map that is not only technically reliable, but also clear, readable, and useful for real-world planning and communication. Before we dive deeper into the topic, let me briefly introduce ourselves. My name is Nick, and I am the founder of Scanflow Solutions from Germany. At Scanflow Solutions, we focus on turning complex spatial data into practical workflows and usable results, from capture in the field to processing, analysis, and final delivery. And joining me today is my colleague Andrei. He is a GIS engineer and an absolute expert when it comes to transforming spatial data into clear, readable, and visually effective maps. Together, we want to show you how terrain data can move from raw capture to a result that is both technically strong and visually meaningful. To understand why contour maps are still so important, it helps to take one step back. Terrain can be represented in different ways. We can describe it through individual height points, through dense point clouds, through graphical methods, or through contour lines. All of these approaches describe the same surface, but they do not communicate it equally well. Some methods are highly precise, but difficult to read at a glance. Others are visually expressive, but less measurable. Contour maps stand out because they create one of the strongest balances between structure, clarity, and precision. So, before we move into the workflow itself, let us first look at different ways terrain can be represented and why contour maps became such a powerful language for understanding landform. What makes contour maps especially interesting is that the idea behind them is much older than digital mapping. Long before LiDAR, GIS, or digital terrain models existed, surveyors already faced the same challenge: how to capture the shape of the land and communicate it clearly. In traditional surveying, terrain was measured point by point. Elevation had to be collected manually in the field, transferred onto maps, and then interpreted between measured locations. Older maps often represented terrain with spot heights, hachures, shading, or hand-drawn relief. These methods could be visually impressive, but they often depended heavily on interpretation and were not always easy to read in a precise and measurable way. Contour lines changed that. For the first time, terrain could be translated into a structured visual language, one that made slopes, ridges, depressions, and elevation changes much easier to understand. So, even though our tools have changed dramatically, the goal has remained the same: to make terrain readable, and that is exactly why contour maps remain so relevant today.
So, if we look back at the history of terrain representation, one thing becomes very clear: the goal has not really changed. We still want to capture the shape of the land, understand its reliability, and translate it into a form that others can read and use. But what has changed dramatically is the way we collect that information. As today, instead of measuring terrain point by point, we capture data using mobile laser scanners equipped with GNSS antennas, which allows us to record point clouds in a precise and georeferenced way. Now, with FJD Trion scanners, we are able to collect very large amounts of spatial data quickly, efficiently, and with a high level of accuracy. And these measurements create a highly detailed foundation for all kinds of deliverables. And of course, that includes contour maps. But even though the data capture process has become much faster and much more powerful, the raw data itself is still only the starting point. A point cloud in its raw form is rich in information, but it is not yet ready to become a meaningful terrain product. So it first needs to be prepared, structured, and brought into the right form. The good news is that with the right tools and the right workflow, handling these large data sets is not really as difficult as it may seem. So let's now take a closer look at the process that happens in Trion Model after the data set has been captured in the field with FDD Trion scanners.
Now let's move on to the next slide and look at the workflow inside Trion Model. The first step is point cloud mapping, which we use to process the captured data in Trion Model. To georeference the dataset in the desired coordinate system, we use the GNSS fusion function. This allows us to accurately position the captured data and work with a georeferenced point cloud right from beginning. Once that is done, we move on to automatic classification in order to extract the ground points. Of course, no algorithm is perfect in every situation. So the next step is to review the result carefully. Using manual classification, we can correct and refine points that were classified incorrectly. In addition, we can use different clipping tools to manually remove any points that do not belong to the terrain surface. For example, buildings, stockpiles, vehicles, trees, or other objects that will interfere with the terrain model. The goal at this stage is very clear. We want to end up with a clean point cloud that contains only the relevant ground points. Once we have that, we use data extraction to export the point cloud by class and create a new point cloud containing only the selected ground points. At this point, because we have removed disturbing elements, such as buildings, trees, vehicles, or stockpiles, there will be naturally gaps in the dataset. And to close these gaps, we use the triangulation function based on the classified ground points. Trion Model creates a mesh that generalizes and closes the missing areas. This gives us a continuous surface model, and in other words, a digital terrain model, which can also be used for many other workflows as well. And if needed, we can first reduce the point density slightly by using the sample function. This helps the generated mesh to be lighter, reduces file size, and avoids unnecessary strain on computer resources. Once the mesh has been created, we then use the subsample function to generate a new point cloud on the surface of that mesh. Here we can define a suitable grid resolution to keep the dataset efficient and well balanced in terms of detail and file size. The advantage of this triangulation and resampling workflow is that previously empty areas now receive new points based on the generalized terrain surface. In other words, the holes are no longer empty. They become part of a continuous terrain dataset. As the final step in Trion Model, we use the orthophoto function to generate a digital elevation model in .tif format from this new subsample point cloud. What Trion Model creates here is a raster image made up of pixels, and those pixels store the exact elevation information derived from the point cloud inside the alpha channel. This raster can be transferred into QGIS, where it becomes the basis for generating the final contour map. So now let's dive into Trion Model and have a look at the full workflow inside Trion Model. So this is the processed and georeferenced point cloud we get after we hit the point cloud mapping. In order to check whether the point cloud is georeferenced or not, we have two options. The first one is if we hover on top of the point cloud with our mouse, we can see down here the location, showing us the coordinates of those points. And the other one is to pick from the toolbar on the right side of your screen, go to measurement, pick a point, and then we just pick a point and then verify whether the point cloud is georeferenced or not. When we are choosing point cloud mapping, we need to go for GNSS Fusion and choose for our coordinate system we want the point cloud to appear. In order to have the point cloud georeferenced, the second way is after we process the point cloud, we can go to GNSS-based registration and choose the coordinate system right here. So after the point cloud is processed, the first step we need to do is to go to the Edit tab and hit Automatic Classification. And we choose the Outdoor classification, and we want the ground classification right here. So I will uncheck the other two checkboxes here. Then we choose the ground type. For this scenario, I would choose a gentle slope. The ground thickness, I usually set the ground thickness to 0.10 meters. And the extraction accuracy, I'm lowering this down to 0.5 approximately. You can actually play around with those values in order to get your result as much accurate as you want it to be. And then we hit OK. After we hit OK, we should get the ground points classified. I did this on this point cloud already. I will show you how the classification looks like on this point cloud. Going to the display tab, we can change the display color of our point cloud. I choose classification in order to display this point cloud by classification. And as you can see here is I already classified the buildings and some noise points, vehicles, some stockpiles over here. And what you will get is after the automatic classification for the ground points, you'll actually get classified point clouds. And the next step is in the Edit tab, you go to Data Extraction. You choose Data Extraction. Make always sure, by the way, make always sure to apply the right point cloud. You can check whether the point cloud is applied by those yellow box around it that appears on your screen, or this light gray background color. So if I choose this point cloud, those lines, those yellow lines disappear because I am now activated this point cloud. So make sure to click on this point cloud and then go to data extraction. We do not want a height-based extraction. We do want to extract by category. Here we can choose from our classes that are defined inside this point cloud. You will have something like unclassified and ground points, and you will just uncheck everything except the ground points and then hit OK. Now, after you've done this, you will get a new point cloud in your project files here, and the point cloud will appear. So what you will get is a point cloud that looks something like this. Yeah, exactly. So what we see here is the extracted ground points. And as you can see here, we have the gaps between the terrain because we deleted the building here. We had some trees over here, here, and here. We had a fence here, and stockpiles over here and over here. So we have gaps inside our data, and those gaps does not contain any information, obviously. So if I hover with my mouse around here, we can see down there the coordinates. And if I hover with my mouse over here, we don't have any information here because obviously there are no points. And the next step will be to create a mesh that fills all of those holes to get a nice and smoothly infilled digital terrain model. And you can use, if you have some noise points and want to clip out some trees, I can show you how I am doing it. So I display the point cloud not in a perspective, but in an isometric way down here, over here. Then I'll hit this top view, and then we can use the clipping tool that is right here. Oh, I chose the wrong point cloud, as you can see. Let me go back one step, choose the right point cloud, should be this one, and then hit clipping. Now I choose polygon here. Now we can go and cut out elements and points that are not belonging to the surface by choosing clip inside. Then those points will be clipped out, and we can hit the check with the trash bin over here to delete those points. So I did this already, and the next step will be to create the mesh. We go to the Edit tab, go to Triangulation, choose the thin triangulation, and the filling threshold should be 0.0, and this will close any of those holes you see here. So after we hit OK, we will get a surface model that looks like this. Let me uncheck the box here to hide the point cloud, so we can only see the digital terrain model we created. As you can see here, our holes are created. So this is how it looks like, and it is quite detailed. As long as your point cloud is detailed, your terrain model will be detailed as well. And in order to optimize your mesh, you can use the size of the file of your mesh. You can use the sample tool. You can find it on the Start tab under Point Cloud Processing, Sampling. And you can sample your point cloud, for instance, distance based, and choose, for instance, 0.1, hit OK, and it will process and delete any points in between the point clouds that are less than or more than 0.1 centimeters, less than 0.1, sorry. And this will reduce the point size and will perform a faster and lighter triangulation. So at the end, you will get a digital terrain model that is much more lighter, but you will also have a less detailed terrain model. So let's wait until it's finished processing and have a look at the result. So here's some new point cloud, and as you can see, it is not as dense as the previous one. So if we compare this both, this is not as dense as the other one. And now we can triangulate this point cloud as well to create the surface mesh. But as we did this before, we will now move to the next step. So we hit we choose the digital terrain model over here, the mesh. And now we need to create a new point cloud on top of this mesh. And now we have to create a new point cloud on top of this mesh. We use the Edit tab, choose the mesh, go to Triangular Mesh, and choose Sample. If we will have uh, some points here that we don't want to be here, we can also smoothen this mesh. So the button smooth will actually smooth your mesh, but you will also lose some of accuracy. So I go to sample and I choose for the sampling method, I choose grid and hit for the grid resolution 0.2, for instance. Now it will create a new point cloud on top of my mesh. And as you can see here, this point cloud is now filled the holes that used to be previously here. So next step will be choosing this point cloud, going to the Start tab, go over to Orthophoto, and now we need to adjust the displayed scalar by height grid values. This will make sure that your point elevation will be transferred into the alpha channel of the .taf file we will export from here. And we can actually go and hit preview to have a look at the result. And as you can see here, we have a lot of gaps in between pixels. So those dark areas inside here are gaps without any elevation informations. So your terrain model will also have gaps if you'll use this for the next steps inside QGIS. And in order to remove those gaps, we need to adjust the edge length. For instance, we can play with those parameters here with this number. We can hit preview. You see there are less gaps now. Now what I like to do is lower the grid size in order to improve the image size. So by lowering the grid size, this also helps to close the gaps. We can hit preview to have a look how it will turn out. You still have gaps. Need to go on preview. Still having gaps. Then adjusting this value, hitting preview. We need to do this as long as we need until all gaps are gone. So as you can see here, we have a very large detailed .tif file without any gaps. Now we can hit export and export this as a .tif file on your computer. So this is basically the full workflow for preparing the data for the next workflow inside QGIS. And the next workflow, my colleague Andre is going to share his screen and show us how to proceed inside QGIS. Let's have a look. Now let's move into the final part of the workflow and take a look at how we continue in QGIS. At this stage, we already have the processed elevation raster that we created from the point cloud in Trion Model. What we want to do now is convert this elevation information into contour lines and then refine those lines so that we end up with a clean, readable, and visually effective contour map. So the first step here in QGIS is to load the generated raster and use it as the basis for contour creation. We take the elevation model derived from the laser scan and transform it into line work. In other words, we convert the .tf file into contours. This is the point where the surface begins to turn into a classical terrain representation. Once the contour generation is complete, we can close that step and review the result. At this point, we can already see that the contours have been created successfully. However, the raw output is usually not yet the final result. We want to represent it. It still needs to be changed and cleaned, adjusted and clipped to the actual area of interest. So the next thing we do is trim the contour lines. And to do that, we first create a boundary that defines the area we want to keep. This clipping boundary can be drawn manually or derived from another layer, depending on the project. In this case, we create a contour polygon that we can use to cut the line work to the required extent. As always, one important point here is the coordinate system. We need to really make sure that all layers use the same spatial reference system, and the contour lines, the clipping boundary, and any additional reference layers must match correctly. Otherwise, the geometry will not align as expected. So we check the coordinate system, make sure everything is consistent, and then continue. And once the clipping boundary is ready, we use it to remove everything outside the area of interest. This is an important cleanup step because it immediately makes the line work more focused and project specific. After clipping, we finish the process and save the result. The contour lines can be stored in almost any common vector format, depending on what is needed later in the project. For example, we can save them as a shapefile, geopackage layer, or another standard GIS format. At this stage, the geometry is already much more usable, but there's still more refinement to do. A typical issue after contour generation is that the dataset contains a large number of very short contour segments. These are often caused by small terrain irregularities, interpolation effects, or local noise in the data. Technically, they may be correct, but visually, they often do not improve the map. In many cases, they make the result look too busy. And so the next step is to identify these short contour segments and remove them. To do that, we calculate the line length and then apply a filter. For example, we may decide that any contour line shorter than 20 meters should be removed from the final map. The exact threshold depends on the project scale, the contour interval, and the desired visual clarity, but the principle is always the same. Reduce unnecessary visual noise while keeping the terrain structure readable. So here we calculate the length, review the result, and then remove the contours that fall below the minimum threshold. And once that is done, the contour pattern already becomes much cleaner. What remains is more readable set of lines that better communicates the landform. After cleaning, we move on to symbology. This is where we begin to distinguish between different types of contours. Normally, not every contour line should look exactly the same. In a readable contour map, we usually separate the main contours from the intermediate contours. For example, every second contour or every fifth contour can be emphasized visually, and this creates a hierarchy in the line work and makes it much easier for the viewer to orient themselves on the map. So we go into the symbology settings and define how the contours should be displayed. We can adjust the line thickness, color, line style, and the interval at which certain contour lines should stand out. In many cases, index contours are shown slightly thicker than the regular contour lines, and this gives the map more structure and makes elevation changes easier to follow visually. So in this case, we also work with the rule-based styling that allows us to define which contour receive a different appearance depending on their elevation interval. For example, a contour that value that is divisible by a certain number can be displayed differently from the other. So this kind of visual logic helps separate the major contours from the minor ones. We create also we create and can also adjust the thickness of the line work. We can also adjust the thickness of the line work further until the balance feels right. If the lines are too heavy, the map becomes too dominant and difficult to read. If they're too thin, the terrain structure becomes weak. So this is really about finding a good visual balance. In addition, we can decide whether the contour lines should be solid or dashed, depending on the cartographic style we want to create. In most cases, a clear, solid line structure works very well, but the styling can always be adapted to the purpose of the final deliverable. And next, we can improve the visual result even more by working with the masking and label support. For example, if labels are used later, masking can help keep the text more readable by preventing line work from interfering visually with the annotation. This is especially useful in denser areas where many contour lines are close together. So we can also apply some slight visual smoothing or refinement if needed, depending on how the source data behaves and how clean we want the final map to look. Again, the goal is not to distort the terrain, but to make the representation more readable and easier to communicate. And once the line work is styled, we move into the map layout, and this is the stage where the GIS result becomes a finished presentation product. We create a layout, define the paper space, and choose an appropriate map scale. In this example, we may work at something like 1 to 1000 scale, but of course the final choice depends on the project size and the intended use of the map. Then we place the map frame, adjust the extent, and make sure the composition works visually. We can also add a title, basic text, or additional map elements if needed. And at this point, the contour map is no longer just a processing result, it becomes a communication tool. Something that can be used in planning, coordination, documentation, or presentation. And finally, once the layout is complete, we save and export the map, and that gives us the final result. So to summarize this QGIS stage, we start with the elevation raster, generate contour lines, clip them to the relevant area, remove very short contour segments, create a clear visual hierarchy through styling, and then prepare the final layout for export. So this last part of the workflow is where processed terrain data becomes a readable map. And this is really the key idea behind the whole webinar. Not just to generate data, but to turn terrain information into something clear, structured, and useful. So as an addition to this workflow, I want to show what is else possible inside QGIS with this elevation terrain model. You can just place points wherever you want, and those points will actually have the right height value, which is stored inside the digital elevation model you exported from Trion Model. So we just hit place we just place points inside the area that we captured, and we can basically place points wherever we want to, and we will get the exact height value of this point. So this kind of replaces manual measurement with GNSS rover, for instance. This is how it looks like inside QGIS.
Thank you so much, Nick and Andre, for the great presentation and for sharing your practical experience with us. And of course, thank you to everyone who took the time to join us today. We hope this session was useful, informative, and inspiring for your own projects and workflows. By the way, if you have a workflow you would like to share in one of our future webinars, we would be happy to hear from you. Please reach us at mkt@fjdtrion.com. Innovation grows when people share what works, and great workflows deserve to be seen. Thank you again, and we look forward to seeing you at our next webinar. See you next time. Goodbye.